Okay, so last year's exam is going to be very, very similar to this year's exam if you're going to be using that to scale it. And then also I did the 2017-18 exam, and that ended up being quite similar. I've changed it very, very slightly from one year to the next. So in 2017-18, I was very pragmatic and made sure the exam is very closely aligned to what it was the year prior, just because that was my first year doing the course. And then the 2018-19 is a little bit more different. And then this year is going to be very similar to the 2018-19. I should mention that because this would have been something I would have told you if you were still doing the exams at the university, that this year on the front page of the exam, I give a formula sheet. And I forgot to upload the formula sheet to the website. I'll do so, but of course it's now open book. So the formula sheet gives you everything from polar coordinates transformations, spherical coordinate transformations, divergence theorem, Stokes theorem. So this was something that I want to do for this year's exam when I thought it was still done at the university, which is I didn't want you to memorize Stokes' theorem or divergence theorem. And so it would all be given on that front page. Okay, so you'll still see that when you do the exam, but obviously now it's open book. Okay, so this is just, I don't know how helpful writing this out is, but I think maybe it's just helpful because you feel a little bit more at ease when you know what you're walking into. So just to confirm that the exam that you'll be getting has a part A, part B, and part C, and part C was written this year specifically because of the situation. So the exam that we submitted in March, I think, was when we drafted the original exam before the university was disbanded. That is the same exam that you'll see. So everything that we intended to teach is going to appear on that exam. And of course, all the questions that we thought would have been well suited for writing in person is still going to be there. Right? So in many of your classes, you might have questions like cite this theorem or cite this result, which we would have perhaps expected you to memorize. Now you can refer to your book. So that was something that the DOS team decided to make it easier for everybody not to have to draft a new exam. Okay, so that is your part A and your part B, and that's been scaled down to 80%. So whereas before, when you wrote part A and part B, that was worth 100% of your exam, now everything just ends up being scaled by 80%. So if you score perfect on your part A and part B, you'll score 80%. Okay. The part A, mandatory questions, which is listed here, this is going to be very, very similar to mandatory questions from 2017-18 and 18-19. So there's no funny business, as I've said, there's no tricks to this. There's no kind of tricky questions here. These are just very standard questions about the basic topics in the course. So in years prior, you had questions related to vector calculus, state certain theorems, calculate certain Fourier series, and so you can expect questions of the same sort this year as well. Now for the part B questions, you have to pick 2 of 3 questions to do. I'll get to that question in a second. For part B, you have to pick 2 of 3 questions. So in fact, the structure that you see here, the question 1, 2, and 3, is almost precisely the same as the structure for the other 2 years of exams that I did. The first question will be purely about vector calculus. The second question will be about heat flow and Fourier series, and the third question is about the wave equation. Okay, so the calculus element of the first question this first question will be confined to just vector calculus. There's not going to be any heat equation or wave equation theory in this first question, but as part of question 2 and 3, because you end up using vector calculus, things like the divergence theorem to prove, for example, the formula for the heat equation or the formula for the wave equation, then of course there will be vector calculus elements in questions 2 and 3. And then finally, the open question, I've not given you many details about this. This will be something that's going to require you to write in a technical manner. So it's not quite an essay, right? It's not just words. You're going to have to use mathematics, but it's not a computational question. There's not going to be a compute this formula or a prove this theorem. It's going to be a, think of it as an expository question. It's the question that I've asked you to draft a response to a given topic or a given question, and the response that I'd like you to draft is the kind of response that would be well suited for example, a mathematical expository journal, right, or a newsletter, right, or something of that sort, where you're going to use mathematics that you've learned in this course to justify your answers, but there's no computation, there's no theorem proving, okay? And I've decided not to give you more hints than that of what the open question consists of. But again, it's the open question. I've not drafted it to be particularly tricky or particularly, there's no funny business, if you like. It's a question that I think I hope that you would have an understanding of by the time you've gotten to the end of this course. One question in the chat is it worth doing all three Part B questions? My understanding is, and I don't think it's something that I have to confirm, but in the past, we would mark the top two questions. So if you chose to do all three questions, we'd mark the top two questions. I'm essentially sure that we'd keep the same format. So you're free to do all three questions, and then we would pick the top two. If we aren't allowed to type the answer, how do we keep it within the 500-word limit? Okay, so this is an interesting point. Originally, when I drafted the exam, we were asked to give some guidance of how much to write for this Part C question, and I wrote to the board or someone from the board, and I said I'd like just to say that you have a 2-page limit. But then the problem was they said, well, it's very hard for some students have large writing, some students have small writing. So it's not so clear if you should say a 2-page limit. My understanding is that the DOS team might give you some additional guidance of how to consider a word limit in your answers. So this is something that they promised in an earlier email, which was, how do you count words in maths? I don't think it's essentially anything that is strict. Obviously, we're not going to go and count your words, but it's just more of a guidance to help keep our job simple. Yeah, that's right. So yeah, it's not something that we really care about, but it is just, I think, important to clarify that it's, roughly 2 pages. So when I thought about 500 words, I wrote my solution to the problem, and then I just counted the number of words, just copied and pasted that minus the mathematics. And that's around 500 words. 500 words is about 1 full page typed in computer font, and then I think around 2 pages handwritten if you have fairly moderate handwriting size. There is no definitive right answer for the 20%. I mean, we've given a model solution for that, but it's quite flexible. Basically, the 20%, if I can just be honest, the 20% is a way that we have to help scale the solutions, because I think we're all worried about what's going to happen. For example, if everyone just scores 100% on Part A and Part B, there has to be this additional question to help separate, the first class and 2 ones, and so forth. Or alternatively, if for whatever reason students do really poorly because the structure of the course made it very difficult for them to study, then that extra 20% gives us the freedom to help scale the marks in a positive direction. I should just mention that the university is still looking to clarify the no detriment policy. So I believe that they have written documents for the no detriment policy for the finalists, but they still have to clarify a little bit for, in your case, for the case of the second-year students. Okay, let me very quickly go over the spreadsheet that you have. So this is the spreadsheet, and it's divided into 3 topics for this course. There's the vector calculus bit, there's the Fourier series bit, and there's the PDEs bit. So make sure you access the tabs at the very bottom of the exam study guide. I've loosely classified the topic into priorities. So a priority of 0 is basically you don't have to know it at all. This is something that I wrote in here previously, that all such concepts have a minimum priority rating of 1. Except if it's removed from the course. So basically anything that I've done in lectures is fair game unless I've explicitly written a 0 in there. Priority 3, I've tried my best not to actually tell you what these numbers mean, so it's up to you to interpret what 0, 1, 2, 3 means. But I think very loosely in my head when I say 3, I mean that it has definitively come up in this year's or last year's or the years before one of the previous year's exams in a more of a central role. So a question, for example, 3 here, define the vector equation of a curve, the tangent vector. This is just a fundamental topic or a fundamental definition or method that you have to know that has basically impacted any vector calculus question in the last couple of years. So this is what the 3 means. So on the right hand, I've added in this little change column here where I just point out things that I've changed from last year between the 2 spreadsheets, from the last year's spreadsheet and then this year's spreadsheet. So for instance, this year, there used to be a component in the chapter 2 notes about this extra technique of proving vector formulae. This using index notation. This has now been moved to the appendix, and I don't expect you to read it, though I think it's good for you to know that such techniques exist. So this is why this has been downgraded to a 0. What other changes are there? I've clarified in certain parts things like discussion. So if you look at this type column, I've written things like discussion elements. So there's a discussion element here on line 35. Discuss why the surface integral formula is what it is in terms of the surface patches of area ds. So when I drafted this, when I redid this spreadsheet for this year, I've added in some additional comments into that section. So that's why you see the yes for here and for there, okay? In some cases, for the discussion elements, you'll see that this year I've clarified the type of understanding that I would expect you to have. So explain the intuition of the proof of the divergence theorem. We did prove it in the lectures. You remember we split it into a top surface and a bottom surface and then looked at the flux through the top surface and the bottom surfaces. And I wrote down the precise lecture number, and I just said, in terms of your understanding, my expectations that are you able to explain this to a friend? So not to the extent where I'd expect you to duplicate the theorem, but are you able to explain the main ideas? So this is often what I mean by a discussion type element. And similarly for Stokes' theorem, this was a theorem that we didn't prove even in full. We did it for the divergence theorem. For the Stokes theorem, we gave a very basic introduction during the lecture of why you can consider the theorem to be intuitive. This was still a difficult theorem, and I don't expect you to know the proof, but I expect you to again, explain the basic idea to a friend. Okay, so that's what I mean by a discussion type question. Moving on to topic number 2. So this is about Fourier series. And you'll see that I've made slight changes to the discussion element of item 20 here. Explain what modes and spectrum means. Explain why convergence is a tricky aspect of Fourier series. This is something that I covered in the last 2 lectures, what the concept of a spectrum is, and we've used the idea of modes throughout the course. And I've added this additional section. So this year I did a little bit more service to this chapter 13, the maths of music, and I've added in this additional line 29. So this line 29, this item 29 for chapter 13, did not used to be there. This is something that I've added in this year. I point out there are no problem set questions for this, but again, this is something that you should watch the lectures, you should read your lecture notes, and your level of understanding is, again, something in which you can explain it to a friend, some of the ideas and the concepts that we've covered. Okay. Finally, for topic number 3, this was about PDEs, so doing separation of variables in Fourier series for the heat equation, for the wave equation, and then finally doing uniqueness, which is the very last topic of the course. So we covered it second to last. The main changes here is an elimination of certain topics. So firstly, I explicitly point out that you don't need to know chapter 17, which is on separation of variables for Laplace's equation, except for what we did together in question 4 and problem set 8. So that was the one where we did the solution of Laplace's equation for a disk. Okay, and we did that, I think, well, we definitely did that in one of the videos, recently. And then finally, for the uniqueness element, I've removed Poissons' equation. So previously, you were expected to prove uniqueness for 3 types of equations: the heat equation, the wave equation, and Poissons' equation. And this year, I'm not requiring you to know the proof for Poissons' equation. If you're looking at previous year's exams, then this means that in certain previous year's exams, they had asked you to prove uniqueness for Poissons' equation. And again, that's something that you're not expected to do this year. There's no reason why I've done this other than the fact that I don't think just because I think it's a weight off your shoulders. But it's not a hard thing to do. You use the same type of techniques. I knew that I wasn't going to have as much time for these video lectures to cover all 3 proofs, which is why I've removed it. Okay? And that's basically it. Any questions before we go on and just talk about problem set number 10? Okay, doesn't seem to be, but I'll keep an eye on the chat otherwise. Let's turn to problem set number 10. So problem set number 10, very last set of this course, is essentially all about proving uniqueness. So the topic is energy and uniqueness. And I spelled uniqueness. I have a habit of spelling uniqueness wrong, apparently. So I've forgotten to put an E in there. And you're asked to prove uniqueness for the 3 types of equations, but as we said, you're not expected to do Poissons' equation this year. So you just want to be able to prove uniqueness for the heat equation and for the wave equation. The 2 variants that you should know is how to prove uniqueness for the heat equation, the wave equation in 1D and in 3D. Right? In theory, you can use the 3D proofs for the 1D version because it's the same proof. But because the chain rules and the vector operations are a little bit simpler in 1D, it's good to know how to do that directly in 1D. So we did it in lectures directly in 1D, and in this problem set, you're expected to do it in 3D. Okay? And you're asked to essentially prove uniqueness for those 2 types of equations, the heat equation and the wave equation, with the standard initial conditions, and essentially the 3 types: the Dirichlet condition, the Neumann condition, and the mixed condition. And the techniques that you use are going to be very, very similar between all 3 types, or all 2 types if you only did the 2. And we'll talk about them now. Okay, so I've written the problems on the board here on the very right. This is basically what we want to do. We'll get in as far as we can. We want to do the heat equation, prove uniqueness of the heat equation for the 3 boundary conditions. We did them already. Well, we did parts of it already in the lectures, but I want to do it properly in this problem set 10 version. And then for the wave equation, again, wave equation in 3D, initial displacement, initial velocity, and then the 3 possible types of boundary conditions. We haven't covered the mixed condition. I wrote R here because sometimes it's called a Robin condition. I'll write an M here for mixed condition. And in the problem sets, you're given the additional restriction that A and B have the same sign. Okay, so A and B have the same sign. Is positive. So A over B is positive. Okay, you can't quite see it behind the ticker, but it says A over B is positive. Right, so there are a few things we need. There's a few tools that we're going to need to prove the uniqueness for both of these elements. And it's worth me just repeating them and writing them clearly at the very top here. Okay, the first thing we're going to need is the divergence theorem. So just to remind you what the divergence theorem is, you're going to need to know that the triple integral of the divergence of f is equal to the double integral over the boundary of f dot n ds. Okay, that's the first thing you're going to need. That's going to basically allow us to integrate in the volume and then convert them to integrals over the boundary to use our boundary condition. The second thing we're going to need is, I'm just going to remind you what this quantity is, the du dn. So du dn is, by definition of the directional derivative, it's the gradient of u dotted with the normal direction. Okay, so that's how you calculate the rate of change of u in the normal direction. Whenever you see du dn, you just think of this right-hand side. The next thing you're going to need is a formula for the chain rule, or the product rule. And the formula is that if I take the divergence of u grad v, this is grad u dot grad v minus u times the Laplacian of v. Okay, and you end up using this kind of formula with a different choice. So the u here is not going to be the same as these u's. For the heat equation, you'll use a version of this, and for the wave equation, you'll use a slightly different version with a time derivative instead. Okay, but this is just the product rule for the vector calculus form. I think that's basically all we're going to need to prove those two results. Okay, so the first step is always going to be the same. You're going to set up a W, which is the difference between two possible solutions, a U and a V. So you're going to let W is equal to U minus V. Just to be clear, I'm not going to be able to write a full solution with the proper presentation, just because I don't have space. But when you do this properly, look at the solutions, look at the way the solutions are presented, and look at the way your lecture notes are presented to know how you should present a proper solution. So let W be the difference between U and V. U and V are our solutions. And when you substitute this W and this definition of W into these formulae, what's going to happen is that you find that W satisfies the same two equations. W has zero initial conditions, so this will be W of x0 is equal to 0, and W and Wt is equal to 0. And finally, W will have zero boundary conditions for each of these versions of the boundary condition. Okay, so I'm going to go ahead and do that, replace the U and the V formulas with the problem that I'm now trying to solve for the W. When you substitute it in, you'll find that these are all changed to W's. And as we said, it's going to zero out the boundary conditions and the initial conditions. And these are all now W's. Okay? And then the same thing for the wave equation. Then you take the PDE, you multiply by an appropriate factor, and integrate over the domain. Okay? So you take the PDE for the heat equation, you multiply by the appropriate factor, in this case it's a W. You rewrite the time derivative here as 1/2 Wt squared, sorry, 1/2 ddt of 1/2, and this becomes a W squared. And then you integrate over the volume. So now I have ddt of the integral over the volume of 1/2 Wt squared is equal to kappa times the integral of W Laplacian W dt. Then what you do is you take this right-hand side and you apply the product rule to convert it into a slightly different form. Okay, so you're going to apply the formula that we wrote down for the product rule and erased. And in this case, you want to use the product rule applied to this element here. So if I apply the product rule to this, I have grad w dot grad w plus w times the Laplacian of w. Now I can notice that this w, Laplacian w, is there on the right-hand side. I move this over to the left-hand side and simplify the equation. This, by the way, is just the magnitude of dw squared. Okay? So now in this right-hand side, we're going to take this divergence minus this term here, and then we'll move that term over to the left-hand side. Okay, so this will be this divergence minus this quantity here, placed on the right-hand side, then moving this quantity to the left-hand side. I can't remember what was supposed to happen, so I'm going to keep on going. So we had the divergence of w grad w minus, what did we have? We had the magnitude of w squared like this, dv. I don't quite want to move it over to the other side. I want to keep it here for the moment. Okay? Right. So now I notice that this one here, this divergence of a quantity, is what I need for the divergence theorem. This is my divergence of f. So I can now convert this by the divergence theorem to an integral over the boundary. So that's what I'm going to do. I can do it on the same line here. So this is going to be divergence of f, and then it's going to be an f dot n ds. So this first integral will be converted to a kappa times a double integral over the boundary of v of that quantity dot n ds. Okay? And then this will be left as a triple integral. So we'll keep that there as a triple integral. It'll be a minus kappa triple integral of over v of magnitude of dw squared, like that. Then I notice that dw dot n is just dw dn. That's the formula for the directional derivative. So this is then converted to a w times dw dn, like that. Okay? That's right. Okay, good. So now I'm ready to apply the boundary condition. In the case of Dirichlet conditions, I know that w is equal to 0 on the boundary, so this term goes away. In the case of Neumann conditions, I know that dw dn is equal to 0 on the boundary, so that term goes away. In the case of the mixed condition, something else happens, so we're going to get to that in a moment. But in the case for Dirichlet and Neumann, you now have this quantity here, which you can define as E of t. This is your energy. ddt of E of t, the dEdt, is equal to minus kappa times the triple integral, or the volume, of the magnitude squared. However, this is a triple integral over a squared quantity, so this integral is always positive, and hence the right-hand side is always negative, or less than or equal to 0. Okay? So now I'm going to try to keep this here because I think I'll need it for the mixed condition in a second. So I've concluded that the rate of change of energy is always less than or equal to 0, but I know that E of 0 has to basically be 0. Because E, which is defined as this quantity, of 0 is the initial condition for W, which has been set to 0. So E of 0 is 0. So this essentially tells me that the energy starts off at 0 and it has to decrease, right? Since the energy here has to be greater than or equal to 0, because it's the integral of a squared quantity, then naturally the only way this is possible is if E is equal to 0 for all t. It has to start from 0, it has to be positive, and it has to be less, the rate of change has to be less than or equal to 0, therefore it has to remain at 0. Okay, you have one final step in order to prove uniqueness, which is the following. If E of t is equal to 0 for all t, then necessarily W has to be equal to 0, because this is the integral of a squared quantity. If W is equal to 0, then you have uniqueness. U is equal to V. Okay, so I'll just write that out here. I'm a bit cramped for room because I want to keep this on the board. So you would say that since E of t is equal to the triple integral of 1/2 W squared dV is equal to 0 for all t, then the only way this can happen is if W is equal to 0 for all t. Yeah, for all t and not for all x. Okay, because if it was not the case, then you'd get some sort of positive area here, or positive volume. And so that tells you that U is equal to V, so you have uniqueness. Okay, yes, that's right. So someone's asked, how do you go from dWdn to the formula here? So dWdn is grad W dot n. Okay, this is just a definition of how you compute the derivative of a function in a given direction. So if you go to the initial review, vector calculus review, then it would have essentially confirmed for you that the derivative of a function u, or w here, in the direction of a vector v is equal to grad w dot v. Okay, where v here is the unit normal. So as long as your v is scaled to have unit normal. So this gives you the rate of change of a function in the direction v. You simply compute the gradient and then dot it with a unit, with a vector which has unit dimension, unit length in the direction of v. Okay, so this is just by definition of the directional derivative. Yeah, so whenever I write n, I always assume I'm a little bit bad with keeping up the notation for the normal, the normal n, but in most contexts, n should be a unit normal. Okay, so if you're good, you should write your little hat here just to confirm that this is a unit normal. But whenever you apply the divergence theorem and you have the right-hand side, which is the surface integral, you should always remember that n is a outward pointing unit normal. Okay, so we now have to deal with the mixed condition, and the mixed condition just requires one extra step. So you go back to this line here, and instead of being able to claim that this first term on the right-hand side is equal to 0, you now have a substitution to make either for w or for dw dn. So if I make a substitution for dw dn, so if I know that dw dn is equal to minus a over b times w on the boundary of d, then according to this line here, I have ddt of the triple integral of 1/2 w squared dv is now minus kappa times a over b times double integral over v, the boundary of v of w squared ds, and then you subtract this second integral as well. So the triple integral over the magnitude of w, or magnitude of grad w squared dv, like this. So we've simply made the substitution for this component of dw dn using the mixed boundary condition. But you have the same conclusion you would have if you didn't have this mixed condition, which is that the right-hand side, because this is the integral of a squared quantity, and this is also the integral of a squared quantity, and that a over b have the same sign, this always has to be less than or equal to 0. Okay, so at this point, you're able to go with the same reasoning you went with just a minute ago. That's basically it. It's also an interesting question for you to wonder physically what happens if A and B have opposite signs. And I think what happens there, though I have to think about it, off the top of my head, I think what happens there is that you have energy generation from the boundaries and the whole thing is unbounded. So the heat will increase. W will not be 0 in that case. So if A and B have opposite signs, then something is driving the flow at the boundaries. Okay, so now we're going to do the wave equation. So we've covered the heat equation. You see it's pretty straightforward procedure. Let's do the wave equation. So it's going to be the same type of techniques. The only difference is that the product rule that you've been using for the heat equation is going to change. So we're going to do the same thing and let W be difference between U and V for two solutions. And then that's going to change all your equations from U, a generic U here, to a W. And it's going to zero out all the initial conditions and all the boundary conditions you have. So instead of the initial displacement, non-trivial displacement, you have a 0 displacement and initial velocity. You have 0 Dirichlet or Neumann conditions, or a 0 mixed condition. It is an interesting question physically to wonder, you do get lost in doing the mathematics of these things, and it's important to always keep one step in the physical world. You are trying to solve the deflection of a string W, which is being held pinned at the ends with, for example, 0 height. Start off with a 0 displacement and a 0 velocity. So at least intuitively, physically, you're expecting that solution to just be 0 everywhere for all time and for all x, right? But we're trying to do it mathematically here, trying to prove it rigorously. Okay, so again, you're going to start off with a wave equation, multiply it by a number or a factor, and then integrate over the boundary, or over the volume. And in this case, the factor is a WT. So I'm going to multiply the wave equation by a WT. This is our c squared WT and then a Poissons of W. And then again, rewrite this left-hand side as a derivative. It now becomes a ddt of a WT squared, 1/2 WT squared, and then integrate everything over the volume. So this is now a ddt of a 1/2 WT squared dv. And then we integrate this right-hand side over the volume as well. So we had a WT Poissons of W dv. This. Okay. Then you're going to use a product rule to rewrite this right-hand side. So the product rule that you're going to use is a WT grad W. It's basically what you need for that second component here. This will become a Laplacian W with a WT. You need to match this right-hand side. So you can kind of think about it either this way and make up the function so you get the right-hand side, or think about it in the reverse direction. So this becomes a grad WT dot grad W plus a WT Laplacian of W. And the order of the Yeah, sorry. And you want to rewrite this formula here to be a 1/2 ddt of grad w squared like this. Okay, and you can verify that this has to be the case because I can rewrite this magnitude squared as this. And then if you take the time derivative of this quantity, then it's just the product rule applied to each of the two components. So you get twice of dwt dot dw, and that's why you have the 1/2 factor right here. Okay, so then this becomes, this is just what it was. You move this over to the left-hand side, leaving the right-hand side matching the integrand, and then just substitute it back into the equation. So let's do that now. In fact, I'm going to do it on this line here. So I'm going to move this over to the left-hand side. This will be a minus 1/2, what we say it was, ddt of magnitude w squared plus that, and this disappears. And then now you're ready to substitute this quantity into this right-hand side. And then what we're going to also do is then move this negative over to the left-hand side. I sort of know, I mean, once you do these problems, you sort of know what you have to do. But the basic idea is that you're going to have a kinetic energy plus a potential energy on the left-hand side. So unlike the heat flow problem where you only have one term to deal with the energy, in this case you have the sum of a kinetic energy and potential energy. So you'll have to move this over to the left-hand side. So you move it over to the left-hand side, and it becomes ddt triple integral of v 1/2 wt squared plus 1/2 magnitude dw squared dv is equal to a c squared, and on the left-hand side here, you remember you had that divergence. So this was a divergence of wt grad w. Let me rewrite this properly so there's enough space. Right, good. So now we're ready to apply the divergence theorem. You have the divergence of a vector field, dv. This is then converted to a surface integral of f dot n ds. Okay, so you remove one of the integral signs, convert this to dv, and this is your f dot n ds. Then this you recognize as dw dn. Grad w dot n is dw dn. Again, you want to be careful here. You put the little hat to remind yourself that it's a unit vector. But this is wt dw dn. Yes. Good. Now we're ready to apply the boundary conditions. So we've converted it into the derivative of an energy is equal to values over the boundary. And we have different choices here. These are all w's now. Okay, let's talk about them in turn. Firstly, if w is equal to 0 on the boundary, if w is equal to 0 on the boundary of v, then wt is equal to 0 on the boundary of v, right? Because here you're evaluating points in x, and so you're free to take a derivative in time, because it's just the way the partial derivative works. So under the Dirichlet assumption that w is equal to 0, necessarily wt is equal to 0, and this right-hand side is equal to 0. Similarly, under the Neumann assumption that dw dn is equal to 0, this dwn is equal to 0 on the boundary, and again, the right-hand side is equal to 0. We're going to leave the mixed condition for last as well. But you've concluded then that if d and n, if you have those two boundary conditions, then you just have ddt of the energy is equal to 0. Okay, so unlike the case of the heat equation where this was less than or equal to 0, here you just get to straight up conclude that ddt of the energy is 0, so the energy has to be constant. Okay? If the energy is constant, then it has to be the same as its initial value, but the initial value of the energy is 0, so the energy has to be 0 for all time. I shouldn't have erased that. Well, I just need this right-hand side, so I'm going to leave. I shouldn't have erased that because I need it for the next step. I'll rewrite it here in a second. Okay, so the energy is constant. We've concluded the energy is constant, but I know that the initial energy is 0. Because the initial energy is just the sum of its kinetic energy and the potential energy, and both of those are set to 0. So this tells you that E of t is identically 0 for all t. Okay? I better write this in here. There's a 1/2 Wt squared plus a 1/2 grad W squared. And I don't have space to write the dV. Okay, the step, when I did this lecture for proving uniqueness, I mentioned that students often screw up the very last step. If the energy is equal to 0 for all t, then this integral is equal to 0 for all t. And the only way that can happen is if the derivatives are equal to 0. So if this is equal to 0 for all t, you would come to the conclusion that essentially grad W is equal to 0 and Wt is equal to 0. Okay? So you're able to claim, because there's sum of squares, that the only way the integral of a sum of square is equal to 0 is if each individual element is equal to 0. Okay? And so now you've concluded that W, it has to be constant, basically. For all time. Finally, what does this constant value have to be? Well, you know that W has to be 0 on the boundaries. For the case of the Dirichlet condition, you know that W has to be 0 on the boundaries. I'm going to try and memorize this condition here. Okay, sorry, just making sure here. So W has to be constant for all t. Under the Dirichlet condition, W has to be 0 on the boundary, so therefore W is equal to 0 on the boundary of V, so therefore that constant has to be equal to 0. Okay? Under the Neumann condition, I know that dW dN has to be equal to 0. I just realized that the solutions might be wrong, because under the Neumann condition, you could have a solution in which W is equal to 0, is equal to a constant. Okay, so let me just recap what I believe is to be the case, but we're just going to confirm in a second. For the wave equation with the Dirichlet condition, with W equal to 0 on the boundaries, by the time you get to this step, where you've concluded that W has to be a constant, the only possibility is that constant has to be equal to 0, because W has to be 0 on the boundary, right? So you've concluded that you have uniqueness. However, if you have a Neumann condition, then the only restriction is dW dN is equal to 0. In particular, if you were to look at the wave equation and you just think, do I have for example, W equal to 1 being a solution, you'd see that W is equal to 1 satisfies the PDE. W is equal to 1. Okay. So no, that's right. You have that condition. You have the initial condition. Let me just think about this properly here. Yes. No, that's right. No, the solutions are right. So under the Neumann condition, you have dW dN is equal to 0, and you conclude that W has to be constant, but that constant has to be 0 because it's the only constant that satisfies those two initial conditions. Yeah, okay. But the initial conditions tell you that W has to be equal to 0 for all x and for all t. So hopefully you understood the gap in my logic, because I was trying to think, why is it the case that W equal to 1 is not a solution, but W is equal to 1, even though it satisfies the PDE and it satisfies the Neumann condition, it does not satisfy the initial conditions. So the only possibility for both Dirichlet and Neumann is that W has to be equal to 0, and you have uniqueness. Okay? So the solutions are correct when you look at the solutions. Okay, that leaves us with the very last case, the case of A and B and the mixed condition. And that is probably the trickiest of all the cases because it requires you to redefine what the energy is. Okay, so but once you know that trick, you're able to get it pretty quickly. So I have a 1/2 Wt squared plus a 1/2 grad W squared dV. And on the right-hand side, what was it? No, okay, I remember that. Yeah, okay, I remember. On the right-hand side, I had that. Okay, so now I do the same thing as I did for the heat equation. I move the AW to the right-hand side here, and then I make the substitution for dWdn. So this now gives me minus c squared times a over b times the double integral of dV of W times WT ds, like that. Okay, I think that's right. Okay. And then what I do is I'm going to rewrite this as a derivative term. So I have a minus c squared a over 2b ddt of a double integral of dv wt squared ds. Sorry, there's no square there. Okay, and then finally I move this right-hand side over to the left-hand side and I put everything under the same derivative sign, ddt. And then I'll have a ddt of something equal to 0. So once you take this right-hand side, move it to the left-hand side, then we have one big ddt of plus c squared a over 2b times an integral over the boundary of w squared ds is equal to 0. So I believe that in this case, with the mixed condition for the wave equation, when you consider the energy conservation, you need to include an extra energy that's coming from the boundaries. But this becomes your new E of t. And at this point, you get to play with the same rules as you had before. dE dt is equal to 0. Therefore, E of t is equal to constant for all t. What does this constant have to be? Well, you're free to impose the initial conditions, and you would conclude that this constant has to be 0. The constant has to be 0 for all time, and therefore, because these are all squares of integrands, you conclude that Wt, grad W, and W is equal to 0 for all time. W is equal to 0 for all time in space. And this last condition is enough to ensure uniqueness. So you have W is equal to 0, so U is equal to V. So in all three cases, D, N, and M, you have uniqueness. Oof, that's the end of the proof for these two cases. So it took us a while to get there, and I bungled up that last one. But actually, you see that the techniques are all largely the same. It's pretty simple for the Dirichlet and the Neumann case, and for the mixed case, it's a little bit trickier. For the mixed case, for the heat equation, it was relatively easy because your right-hand side still became a negative. But for the mixed condition for the wave equation, it was a lot harder because you have to redefine the energy to include an extra term. But otherwise, once you know that trick, then it's straightforward. So would there be a third contribution to the answer? So the question is there a third contribution to the energy? I think so. So I think that you have to consider this is a boundary condition to the energy. So you imagine a system where you're forcing, so it's a wave in which you're forcing the boundaries in a particular way. So in addition to the internal kinetic and potential energies, you have to consider the energetic contributions from the boundaries. That's my extent of trying to understand this extra contribution. If you're a mathematician, then you don't think of it in terms of physics, and you just think of it in terms of you've created a quantity, a E of t, which turns out to be constant, a conserved quantity. Okay, so I think that's basically it. We're a little bit over time, 8 minutes over time. Any particular questions before we disband? And you'll still get, I think I'll still be sending out an email just to confirm all the details, that the videos are online and all the sources are there. This is not quite the last time we're going to be in touch. As a general rule, do you multiply by one less time derivative than the highest that appears? So this is a very good question. In terms of proving uniqueness, I don't personally know whether there are universal tricks to what you should be multiplying by. So the first step is to take the PDE and to multiply it by a factor. And so one of you is saying, well, it looks like the factor you should be multiplying is always one less time derivative. I don't know whether that is a universal trick to doing this kind of thing. So given a general PDE, what is the factor you should be multiplying by? I don't know the answer to that. All I know is that this is a very standard way to prove, to derive the energy relationships for the heat and the wave equation. These are well known, but for general PDEs, I don't know. It's a good question if you had a general time derivative, so a UTTT, for instance, would you multiply by UTT? You can imagine that that trick works because it always allows you to rewrite the left-hand side as the derivative of a squared quantity. But then again, there are not that many physical problems I can think of. There are no physical problems I can think of where you have a triple time derivative. Yeah, there's no physical problems I can think of where you have triple time derivative. I mean, you can have triple spatial derivatives, but the double time derivative comes from Newton's laws, right? That's the acceleration of the quantity. But I can't think of a physical problem where you have a triple time derivative. Okay, I think that's pretty much it. Epsi is somewhere in the house. She's sleeping away. It's too busy for all of you. But let's leave it at that, just because I want to take a break. Thank you very much for attending these lectures. It's been a very enjoyable ride. It's been a very weird ride, but I really did enjoy this little experiment. Hopefully, it's not the last time that we're going to do this experiment. And I think it worked quite well. One thing I should just mention before I disband, and I will mention it in the email to send out to you, is that you all have to write surveys so you're all encouraged to write surveys for your courses. And I would encourage you to do the survey. So there's a survey that you do on Moodle for all your courses. I would encourage you to do the survey for this course for the following reason. So you'll notice for this course, you did get handouts. You got your textbooks, your printed textbooks. This is a little bit atypical, and also things like these videos. So at the start of the year, I always try to ask the department to give me money to do some of these things. So I tell them it's very useful for me to print out the course textbooks for the students. And there's always a little bit of a fight for them to say, well, do you really need to do that? This costs a lot of money. And it's always good for me to say that they explicitly mention in their surveys that they found this useful, or they find this or that useful. And that actually allows me to get more for you. Or more for the next year's students as well. So any comments, any useful comments that you can provide on the surveys, we do use these. We print them out and give them to the people who dole out the money, and this allows us to improve the courses in future years. Otherwise, thank you. I'll look forward to making the video on sneezing, and I hope that we stay in touch as well. Even after the end of this course, some of you are going to come back in third year to take some of my courses. And so I'll look forward to that. Thank you very much. Have a good weekend, and we'll talk soon.